Okay, so let me start by telling you a little bit about what I have been working on and what many other machine learning people like me have been interested in is to design an AI system that can learn like humans, like us, like animals and other living beings. And when I say that, what I mean is that we want the machine to be able to quickly adapt to learn new skills and keep doing that throughout their life, continue to collect new experiences and learn from them and improve our understanding of the world. And humans are extremely good at this. And this is my daughter. I usually show this video to motivate people of what I'm talking about when I say humans are extremely good in learning, is that we learn from the day one when we are born and we collect experience about the surrounding and we kind of figuring out what we like and dislike in the world. So here, my daughter is sort of slowly figuring out that she really likes the fretboard and the sound that comes from it. She doesn't really understand right now, so she goes away from it and trying to see what she really is into. But after 6 months, she keeps doing this sort of, random exploration, which appears to be. But eventually, the attention converges to some important things for her that she thinks are important in the world. So in this case, it's the sound that she's drawn towards. Not only this, humans are extremely good in like using their past experience for the future. So that's another amazing ability that humans have. So here, she's gone from a smaller instrument, ukulele, to a bigger instrument, which is guitar. And she cannot like quite hold it in the same way, but she's figured out a way to get the same experience out of it because she likes that experience and she's figured in the past that this is what I want. And she's able to somehow get it from the world. And this is the amazing thing about human learning that is lacking currently in machines. So if you think about this kind of adaptation in machine learning, machines are really, really bad in adapting to most of the changes that are being done to their surrounding. And their surrounding means their training frameworks. And if you change slightly some setup, like you change the data, or you change your loss function, you change your model slightly, you don't really have a way to just quickly kind of make a small change. You have to do a retraining from scratch. Right? This is a big problem. So current practices, because of this, they become very expensive and time consuming. And I give this example of Tesla AI data engine, which is really kind of trying to pool a lot of data from all over the world about maybe accidents, some other things that the data could be useful to put together. And for that, they have to always do an update of the model. And often this update requires retraining, and that takes like a lot of GPU compute time, and it's very costly and it's very bad for the earth. So of course, we want to go beyond this kind of static setting to more dynamic setting where things are changing. And then kids are extremely good at it. We are extremely good at it. We can learn about something in the morning, and now you're learning about something else. You're going to learn something else tomorrow. And in this changing, your past knowledge doesn't just collapse suddenly. So this kind of thing also appears for machines quite a lot. So in robotics, for example, in medicine and other applications where the setting is more dynamic, and we want to be able to use machine learning in these kind of settings. Now, currently, if you apply the techniques in these kind of dynamic settings, you change it slightly, and it's just everything just goes to hell. Right. So I mean, this is not really machine learning because probably this robot is not using that machine learning, but I wanted to show that robots need to quickly adapt when things have changed, like furniture is moved from one place to another place, or toys are everywhere, kids are playing with it, and a robot is going around maybe cleaning the house. And small changes in the surrounding can just suddenly make them fail catastrophically. There's another thing that happened a few years ago. It was in 2016. So Microsoft put out this tweet. It was a bot on Twitter called Tweets, and it was supposed to learn from other people's tweet and kind of adjust to what they're saying. But I think it was really towards like adapting too much. So it really adapted and learned and became crazy and started saying some really crazy stuff. Right. So there's a lot of this kind of failure where machines right now are not very flexible. They're a very rigid system, while human learning is actually a very flexible information processing system that can accommodate for incoming evidence much more easily than what machines can do right now. So if you talk to many people, they will say, well, big problem in machine learning is really solving this problem. How could machines learn as efficiently as humans and animals? And this is a tweet by Jan LeCun a few months ago. And we want to have like new learning paradigms. And our view here is to really go towards this sequential information processing and adaptation by using this new learning paradigm that are based on Bayesian principles. So the reason why I think that Bayesian perspective is so important is because there are these two paradigms, as I talked about, and currently they're very separate. So humans are doing this lifelong learning from very small data. The world is non-stationary, but machines really require all information at once. Everything needs to be stationary, and the world has to wait while you learn. It has to be a very patient teacher. And if the world is not patient and is slightly adversarial, or even doesn't pay attention to the robot child will completely fail. And I believe that Bayesian principle can help us to reduce this gap between these things. And I believe this because the past research has shown that whenever you try to write a learning problem and formalize it somehow, it just comes out to be Bayesian. So, or something that's very similar to something of Bayesian nature, I must say. This happens in economics, in social science, in psychology, in neuroscience. There's a lot of theories of processing of new data based on Bayesian philosophy, Bayesian principles. But in machine learning, somehow Bayes remains to be an outlier. People say, "Oh, you're Bayesian." Oh, okay, well, nice to know you. It's not something that unifies Bayes. It's not like how it has been in other scientific fields. In machine learning, it's been set as somewhat a specialty. But this is what we are out to change. We're trying to say that there is a bigger, more general Bayesian perspective to machine learning, that in the same way that Bayesian principles unify learning of living beings, learning of agents in many other fields, in machine learning too, the algorithms that are being used, they are of Bayesian nature, they have a Bayesian side. And because all machine learning algorithms have this common principle behind them, you can sort of use it to improve things. And that is where what I want to communicate to you today. So even if you don't get all the details, the point is very simple, is that we want to see machine learning from a Bayesian perspective, see them as instances of this general principle that is trying to explain many different kind of algorithms applied in some narrow setting, like maybe it's done for SVMs, maybe in kernel methods, maybe something to train neural networks, maybe something to do some Gaussian process or some other model like that. But all of these things can be seen as instances of a single principle. So that's the journey that I want to take you to today. And of course, I'll start by talking about benefits of Bayesian principles and why This is a general idea, and this arises in many other non-Bayesian settings that you may not see a Bayesian model there. You may not see probabilities, but still, there it is. Bayes is still there. Okay, so you will see some of these benefits. We'll try to get into some other areas that are connected to Bayes, and then try to go inside looking into what kind of methods are being used in machine learning and how they differ from this Bayesian formulation. And then look at like the solutions that these two techniques will give. And eventually we'll see that the Bayesian technique can recover the solution of what people do in machine learning. So like point estimates is what we call, you don't have a distribution, but you can get those solutions from a Bayesian perspective. And I know that many people have heard this many times, that Bayes is more general. But here, we're going a little bit more narrow and trying to really, derive a particular algorithm. So I call it Bayesian learning rule. And this is kind of an extension of Bayes' rule to learning problems. It's a Bayesian learning rule. And this particular algorithm will show that if you make small changes to it, it will spit out some algorithms that you would expect it to spit out. Okay. And well, I don't know how much time we'll have to get into examples, but let's see how many we can do. But that's my hope. And I'll probably try to convince you some of the deep learning stuff that goes on in algorithms, and also in like implicit regularization and stuff like that. Some of that can be explained by looking into this new perspective that I'm presenting here. Then the last part, I will talk about how you can use all of this to improve things, and I'll focus on uncertainty estimation. I have some other stuff that I can talk about, and if we have more time, then I can do it tomorrow. But for now, I think it's better to just cover, this much material, and we'll see if we are able to go through it quickly. Then we could do more advanced stuff tomorrow. So yeah, so thing to remember here is that everything is one, and we are not trying to prove superiority of Bayesian methods, but rather we are trying to say that the underlying principle is of Bayesian nature, and that should help us. If we are aware of it, then it will solve a lot of our problems beforehand, because we can think more clearly and perhaps use it to improve things. And that's what I want to communicate to you. Okay, so my hope is that I will have more discussions and not just a monologue here, because lots of these ideas, they are very conceptual and they take time to sink in. And I've been talking to people for many years, and I've understood that only through talking we can really learn. So I'm happy to, for you to just interrupt me anytime you want to, or send message in chat if you're shy and don't want to talk. And please feel free to ask questions, and we'll take lots of breaks in between. I hope I remember to take breaks, and I always say that and I forget, but let's do this slowly and discuss and learn from each other. So at this point, if anybody has any question, I'm happy to answer.
Hi, Emtiyaz.
Hi.
Yeah, before you just proceed, can I just get an idea? Does Bayesian networks and Bayesian in general, does it capture causal relations as the underlying principle?
So Bayesian principle, like general Bayesian principle, is kind of very general. So it doesn't directly say that causality is possible, but because the principle, is so general that it gives us, a way to kind of model our interaction with the environment. So people have actually built on Bayesian principles to do intervention through these distributions that you learn. So, you learn this posterior distribution. Sorry, we haven't got at all to that right now, but I'll just say it vaguely that you have some kind of knowledge of what you know, and then a little bit of like what you don't know. So you have a distribution that tells you. And then using the distribution, you can try to question the world to say, oh, I don't know this thing. Can you tell me if I'm right or wrong? And then you can interact with the environment to figure out certain things that are wrong or right. And this kind of goes into causality because you have this distribution that helps you to reason properly. So Julia Pearl, who pioneered this whole field of Bayesian network, they were designed specifically to do intervention. When you remove an edge from your graph, from your model, how much the distribution change, and can you use that change to then query the environment to see if your change was, somewhat grounded in reality. If the reality is very different than what you're thinking, then you'll get a feedback. So that's how, sorry, this is a very general description and I might not be very precise, but this is how it kind of works. We'll not be covering any of that today, but it will help you hopefully to think of that.
Yeah, no problem. I just brought it up because I noticed that coming from an ML background as well, there's always this disconnect in the, trying to reason with causality, from
Yes.
that perspective. So, and
Yes.
it's leaning on distribution and probabilistic reasoning. That's why I brought it up. Yeah, thanks.
Yeah, probabilistic reasoning is fundamental to causality is what I would say. I'm not an expert in causality, so I might be wrong, and maybe people will disagree with me. But knowing what you don't know helps you to reason, is what I would say. Right? So yeah, also Bayesian network is a subfield of more Bayesian, general Bayesian principle. It's just a technique. So that's another thing that people get confused with sometimes. Okay, any other questions?
Hello.
Hi.
Yeah, I'm Darsh, and I am not very strong in the mathematical background of Bayesian perspective to be specific. So what I wanted is if you could give a map, a map of where these Bayesian perspectives exactly lie in sort of the whole AI circle. I know it also has its roots apart from AI, but and if you could give in fact a complete map of where AI and Bayesian interact with each other, and inside AI exactly which parts of the Bayesian we are going to interact with exactly.
Yeah, okay, great question. So I'm afraid I don't know. So it is a very good question, but I think we don't know right now where exactly this will be useful. So people hypothesize, at least in old times, I mean, I wasn't there at that time, but what I figure by talking to people and looking at the history of what has happened in AI, the uncertainty in AI was a big idea in old times. Maybe Wiesen will agree with me, because in old times there was a lot of this thing was actually built using Bayesian formulation, like Bayesian network, for example. It comes in 80s, and even the connectionist stuff, neural network stuff, that is now it's big, but it was originally in 90s when people were trying these ideas out after Hinton came up with backprop, for example. Hinton himself wrote a paper on like minimum description length. It's from 1992, I think. And David McKay, who was a strong Bayesian from Cambridge, he also wrote a couple of papers on neural network and Bayesian philosophies. So there's always like kernel methods, for example, when that become big in the 90s, late 90s, then Gaussian process is the method that Bayesians were putting forward as a, a Bayesian side to kernel methods. So there's always been a Bayesian side attached to techniques. And many times people, say that, oh, this is not possible by Bayes, and they will kind of deviate. But I'm heavily biased. I'm giving a tutorial on Bayesian stuff. So I tend to think that everything has a Bayesian side. And that's basically what we're talking about today. So it's hard for me to say what is and is not covered by Bayes, although there are lots of counterexamples where a pure Bayesian strategy would not work. So of course you require modifications to it, but overall, my belief is that there is always a Bayesian side to many things that we use in machine learning, and AI, I think, goes with it. I cannot really comment on general AI. It's hard for me to. I hope this helped you a little bit. Is there anything else that I can clarify?
That was good enough. Thank you.
Okay. Yeah, hopefully we could talk about this maybe in the end. It might make more sense at that time to look back and see if it is indeed as big as we are claiming it to be.
Yeah, sure. Thank you.
Any other question? Okay.
Yes,
Awesome. So,
Mcemc here from India. I just want to know one thing, from this slide only. What I'm trying to understand is that currently we have a different paradigm like deep learning, machine learning, and maybe deep leaf network and all sorts of things. But the underlying thing is, I think, as you already mentioned, that even though there is a one very what you call well-tested algorithm, but you change certain parameter and new environment and everything, and then it fails. Like robot goes down the furniture, right? And then I see the last line, the impact. No, somebody sent the message. Impact everything with one common principle. So, is the Bayesian learning is one super algorithm?
Well, I'm claiming it to be, but I would be hesitant to say that because the hope is that that's okay. So I would actually really encourage you to read the discussion section of the paper that we will be discussing throughout the tutorial in this Bayesian learning rule paper. And there we kind of write that often when people talk about machine learning, they say there has to be one, optimal or super master algorithm that runs on everything because we all kind of evolved through the same, tree of life. So if same algorithm runs on almost all intelligent brain or brain-like things, then we would expect that, learning should probably happen in kind of one optimal way. There should be one general principle that explains everything. There's a lot of hypotheses on what that could be, but you really see that it always comes down. Well, always maybe a little bit strong, but what I know in many fields, what I have seen, they always look very Bayesian to me. But other people could come up with some other words. There's this thing called Bayesian brain theory in neuroscience, free energy principle, and then also in statistical physics and information theory and in psychology and rationality and all this stuff. So all of these things have very Bayesian roots to it. Now, if there is a super Bayesian algorithm, that I don't know. But principle, of course, it's a super principle. We don't know about the algorithm. And that's the attempt here to get to it.
Hi. So would you say, what do you have to say about the free energy principle being like a large large umbrella under which a lot of the brain works, and maybe even something that can be extended to machine learning?
Well, free energy principle is, okay, I might get into trouble, but I will say it. Free energy principle, in my understanding, is a Bayesian principle.
Yeah, it is definitely. Yeah.
So.
But is it something that can be an overarching theme? Just like if you want to find some sort of an unified version unified theory for something.
Yeah, yes. I think it has a lot of, I mean, it sounds very good, although people have a lot of reservation to it. I'm not an expert, so I cannot say, because I don't deal on the, living things side of Bayes. I'm more onto algorithm side. So I know math, but I don't know if I can explain all living things or non-living things in the world through Bayesian principles, through free energy principle. I mean, it sounds quite good, but many people have many reservations with it. So I would not go out there because I'm not an expert. Did I answer your question, Manish?
Yeah. I mean, this is something that maybe we can take offline. It's also something to do with how neural networks and how the machine learning system itself is. So, I mean, okay, fine. Sorry to go.
All right. Okay. Somebody's saying that these questions should be at the end, so maybe we should move on. It is true that we haven't really got into the Bayesian stuff. So yeah, thanks a lot. So thanks a lot for all these questions, and I hope that it's a good warming exercise for us to feel comfortable and ask questions, and let's do this more. Okay, so I will continue with the talk. So let me start with some motivation of why we should be doing this Bayesian stuff, and also get an understanding of what is Bayesian principle. Okay, so there are many reasons why we should be Bayesian, and I've listed some of these, and my hope would be to go through these examples. So the one that we really use in machine learning, I refer to it as principle of trial and error. And it's an inherently, the way it's posed in machine learning, it's inherently non-Bayesian. Sometimes people say frequentist. So you could think of, if you know some of these frameworks, empirical risk minimization or maximum likelihood principle. And in this kind of setting, usually given a data, when you want to fit the model with parameter theta, you would formulate a loss function that somehow captures your trial and error. So you try something, and then you make a mistake, and that loss function tells you, oh, you made a mistake, right? So that's how the loss function will work. And then you try to minimize this loss function with respect to theta, the parameters of the model, and then you will have one parameter vector. Right? So that's the more frequentist way of formulating it. An example could be regression in supervised learning, where you have an image, say xi, and you pass it through a neural network, and then it outputs maybe a label, and then you can compare it with the true label. In this case, it's a continuous value. So something like a depth in an image, and then you compare it against the true depth, what the error is, and then you take the square of their error and you sum it. And that could be sort of your loss. Sometimes you add slight regularization because models are not identifiable. So many theta would give the same answer, and that will make it ill-conditioned. So you add a small regularizer to combat that. And you would fit this through some kind of gradient-based method. So in general, they take this kind of form that you compute the gradient, then you precondition using some matrix. It could be Hessian, it could be Fisher, it could be some diagonal of gradient magnitudes, like they do in adaptive learning rate. And this will give you one parameter vector theta. So it could be like weights of your neural network, and it works quite well. Right? So this is the non-Bayesian thing that we know in machine learning. And the difference here is that the theta is just one. It's just one parameter vector. It's just one model that is being learned. So I'll call this principle of trial and error as a principle. But there are problems with this approach. And I'm going to try to go through some some things of why, you know, these methods are not that robust, that they may not generalize well. So there are some issues with these things. Let's try to understand that through an example. Okay, so why having one theta is a bad idea is what we're gonna look at. And what I'm showing you here is basically an example where I show you some data points. And so the x-axis is some kind of like thing that's going linear, increasing. Y-axis is some kind of frequency. And so it's something like, you know, 1 in 100, 1 in 10, and then how should I say 0.1. Okay, so somehow the frequency is going down. The event is becoming less and less, you know, more and more rare, right? And you have this data point. So as you go along x-axis, the event becomes more rare. Okay. Now, what I want you to think, like suppose you're given this data and you want to fit this data, then you would, you know, you could use this model. So this is like with one parameter theta, which is kind of giving you the slope that's going down. But there's an alternate model, a second model, that would kind of fit it with two lines, right? So there's a red model and there's a blue model. The red model is just one line and the blue model is these two lines. The question is, which model is a better model? And I do this, you know, I've done this for many years now, and I ask these questions to many people. I mean, it's unfortunate here that we're not in person meetings, so it's hard for us to take a poll and see what everybody thinks about it. But I would ask you to answer this question in your mind, and keep that. And then we will kind of I'll give you more information, and then you can see, you can update your belief after seeing some more hints. Okay, so usually when I ask this question to people, at least beginner in machine learning, they often choose kind of 50-50. So people are confused a bit about which model they should be choosing. And half of them sort of go with blue, other half goes with red. But the reason here is that I've actually kind of cheated you a little bit. So if you're thinking one or the other answer, is because you don't really kind of know the full picture here. Okay, sorry. So there's a question, maybe it's related. Why red? Okay, it overfits. Okay, I like this comments actually. People are saying some things in chat. So if you have actually some opinion, I'm happy to have more discussion here. So, okay, so somebody's saying that we need more prior information. That's a very good point. And some people are saying that red is overfitting. Red is overfitting. Okay. And somebody's saying blue is better. Okay, this is great. This is great. Data might have noise. That's also correct. So yeah, so all of your thoughts are really on the right side, and I really appreciate them. So yeah, you see that when you have only one model, one line to explain the data, there are all these, you know, other issues that you're not aware of. You may not have complete knowledge of where this data comes from, and you may not be able to understand the specific things that are going on here to be able to be confident that this one model that you have chosen is a good model. So somebody's now saying that's Occam's razor, we should choose the simpler model. And then red is overfitting, for those who know what overfitting is. Yes. So let me give you a little bit of more details of why this is this is not so clear. And so I tell you now, actually, this is real data. It's taken from Nate Silver's book, The Signal and the Noise. It's a wonderful book to read if you want to see more Bayesian stuff in action. And the x-axis is actually magnitude of earthquake. So what is happening here is that as you go along the x-axis to that side, the magnitude of the earthquake is kind of increasing. So this side is larger and larger, magnitude of earthquake happens in this side. Now, with this information, I think maybe some of you can at least guess what's wrong with this approach. So you could say that maybe red is better and blue is worse, and you may be right or wrong. But the thing here is that there is no right answer. And the reason lies in the magnitude of earthquake. So, okay, so somebody said in comments, which is a great point, we need more data. Okay, but can we get more data here? Never wrong to have more data. This is great. Can you collect more data here is my question. Would somebody like to? I'm happy if you're just writing in chat, or if you want to speak, I'm happy to talk. Hooray. So somebody said we don't want to have more earthquakes. Well, it's not under our control. We cannot wait for bigger earthquake to happen. So this is kind of the point of this example, is that when deep learning people would say that go out and collect more data, in this kind of setting, you can't really go out and collect more data. And an amazing point is pointed by somebody, is that high Richter scale earthquakes, and sorry, I'm not saying anything, I'm just reading the chat here. High Richter scale earthquakes are very less frequent. So we nailed it. So we got to the problem, we got to the issue that's kind of causing this problem here. You see that the data here is very, very sparse. We have very few large earthquakes, and we should be thankful about it that we don't have very large earthquake. We don't want to be collecting data with such sacrifice, right? For rare earthquakes, we have a lot of more training data, right? So yeah, it's not feasible to collect more data for training in this case. So if you're making a choice of model here, you're in a very difficult situation, because you just have one or the other model, and you now have to pick that. Now, the Bayesian solution to this more data, less data dilemma is to kind of provide some uncertainty with the model. So rather than having one model, let's have a range of model so that the decisions that we make based on these models are kind of confident. So one thing to, for example, think about is that suppose you're a building designer and you're designing the building in, let's say, in Tokyo, and you're predicting like how often these high earthquakes could happen. So I should design for maybe 7.5 earthquake, or should I design for 8? Should I design for 8.5? And the red model is saying that the 8.5 earthquake is happening once in 1,000 years, while the blue one is saying that it should happen in 1 in 100 years. So blue is slightly more conservative, and the red is more overconfident. Some people pointed out that it's due to the Occam's razor overfitting, and that's indeed the case, that if you go to more complex model, it overfits. But nevertheless, a single model cannot solve this problem, because here you don't know anything. You can have a range of outcomes that could go anywhere. And in this case, you might want to take a more conservative strategy. So you might say that bigger earthquakes are more common than what they actually are. So you might want to design for 1 in 10, right? So red is very risky than blue. And the Bayesian philosophy is sorry, I'm going to come to the comment by Darsh just recently, but that's a very good comment. So the Bayesian philosophy now is basically to have many models. And what I've shown here with this green bar, green region, is all possible models that explains the data well, because there's a lot of data here. So they all have to pass through this place, but there's fewer data here. So they may go all over the place. So the variance where you have less data is quite large. So now you can kind of say, well, I want to attend to this region, and maybe I don't want to I want to go into this tail and minimize the possibility that my building will collapse. So I should design for the scenario that many earthquakes could happen in the future. So I might actually take the probability somewhere here, some model here, and design the thing appropriately. So this is is the way the Bayesian principle works, is that you try to reason about what you don't know, what the model does not know. So you don't look at just one model, you look at other possibilities away from your fits. So somebody said that, is this similar to the class imbalance? And that's a great comment, because it's exactly that setting. So you may have, lately people have been commenting on use of machine learning for profiling and for selecting candidates, or finding terrorists and things like that. And that's where this becomes very problematic, because in those settings, you're usually operating here. You have a lot of data for cats and dogs, but you don't have a lot of data for, minority races. Or if you do the experiment in the US, you can do very well in the US, but if you deploy that model in some smaller country where the training, the demographics is different, then that model will fail, right? So these things are not very adaptable, because the method cannot adjust to the quality of the data. So it's very important. And you may actually think that it depends on what you want to predict, but you don't know what you want to use the model for in the future. So at test time, you never have the test set. So I would really want you to think very hard about this example. This really tells you a lot of things that are wrong with our current way, the way that machine learning is being done. Okay, so I will move on because I'm taking a lot more time here, and I'll get to some of your questions. So Bayesian models are better because they're trying to avoid this kind of bias by using this kind of uncertainty. Okay, so let's go a little bit into math of how do you compute this uncertainty, and the method here is that you sort of start with many candidate models, and these candidate models here I've shown with a few red lines, and these models, you don't know if they're good or bad, but you just sample them from a prior that could be something that kind of gives you no information hopefully about the world, and then you use the then you have a model of the data given the likelihood of the data given the model parameter, and maybe you're saying that all data is equally likely, and maybe you're modeling the mean of the data through this this function. Maybe it's a neural network. So this is the likelihood, and then so this likelihood is sort of a score. So it's kind of telling you that this model, this red model in between, it's the most probable model because it fits the data quite well, so it has higher score. But the model that's kind of far, it's not explaining the data well, it's given lower score using this likelihood, right? But right now you don't know, you ranked the model, you know that this model is the best model, but you don't know how much better this model is compared to the model that's in the tail. So you don't know what's the spread of good models that you should be considering. And this is where the Bayes rule kicks in, is that what you do is that you multiply the likelihood and the prior. And the likelihood is a loss function, as you or somebody's asking here. So the likelihood is exponential of the negative loss. So it's kind of derived from the loss function. So you take that and you multiply with the prior. And so you can think of it as you're taking numbers of each of this model and you're summing all of them up, and then you're normalizing so that the scores are all between 0 and 1. So they become probabilities. And so this is called posterior probability, and it's proportional to the likelihood times prior. But what you need really is a normalizing constant, meaning that you need to average over all possible explanation of your data. And if you have a model which is continuous, then model parameters that are continuous, then there could be like an infinitely many models, right? And so this integral becomes problematic. Nevertheless, with the integral, you can get these error bars, and then it tells you that maybe this pink model here is kind of out of the range, so you don't have to worry about that. Maybe you have to worry about some of these choices. So you should be using these choices to make the decision that you want to make. Okay, so it's a global method which integrates over all possible explanations of the data. So it's kind of different from what I showed before, where you were optimizing for just one theta using a gradient-based method. And because you're doing this integral, it's very difficult to compute the integral. Okay. There's a question. Isn't that why?
Emtiyaz?
Yes.
Sorry if I can ask you a question. How do you accommodate different model forms? Say an exponential model or a linear model. How do you accommodate those?
So you would do this through this probability, right? So,
okay,
like, for example, like you can think of like this mean square error to be a Gaussian, where this is the mean, and then you have a variance parameter around it. Maybe it's 1. Does that make sense? So Gaussian, sorry.
No, sorry. How would that accommodate different types of models, say a linear model versus an exponential model, or
yes, I see. So
hyperbola,
linear model would just be, yeah. So you'd just be choosing this function,
right?
So for linear model, you do. Sorry.
Would you change the functions itself? Would you have a range of different functions to try?
No, here in this case, we are doing everything through theta. So f is fixed. The form of f is fixed. So it might be like, so here in this case, it could be like, you know, a piecewise model. Maybe it has like 5 pieces. Okay. And so it might be like, 5-piece model, and it's linear in that 5 pieces. Simplest to think about a linear model with like nonlinear features. So theta transpose, you know, phi of x, like some nonlinear mapping of x, and that will give you something like kernel methods.
Right. Okay.
Okay, great.
All right. Thank you.
Yes, I have a question. So you talked
please.
about Bayesian optimization. In machine learning, we have the grid search for hyperparameter tuning as well. So
yeah, let me. Sorry, let me just. So I never talked about Bayesian optimization.
Okay.
Okay. So, sorry, this is a common mistake. So Bayesian optimization is again a specialized technique for finding global minimum of black box function, and we are not talking about them actually.
I see. Okay, my bad. So
no, this is great that you point that out.
okay, so in that scenario, hyperparameter tuning, it's not going to be the equivalent of how Bayesian would manage choosing the best model, right?
Yeah, I think that's a separate question. So you could do the same thing with hyperparameters. So you could sample them from a prior, and then you can try to score each hyperparameter setting.
Okay.
So like you might have a prior, let's say variance parameter for the Gaussian noise. Okay, here. I hope you can see my cursor. And you want to know if the noise should be very thin or very thick. And you could sample that noise from a inverse gamma distribution. Okay. And then you can try to score each of those and then average over those. So you can compute the posterior probability over anything if you want. But that's all, everything goes through this equation, this Bayes rule. And you can apply it recursively. Yeah, I don't have time to go over this, but I'm happy to, maybe over email or something, or maybe later on, I'm happy to kind of, I can stick around for a bit and explain this to you, okay?
Okay, thanks.
Okay. So somebody's asking more explanation about the green region. I think that's a, yeah, I wish I had more time to go over it, but essentially this region is, if your question is conceptual, then I think I can answer it. So it's here, what I'm showing is basically maybe something like a 1 standard deviation around, you know, these predictions. So sorry, this one is like hand drawn, so it's not really computed using a code, but it's kind of some credible region, you know, of this posterior distribution. That's what that green region is. Okay, great. Okay, random search, that's fine. Fine, great. So great, many questions, and we're 3:57. So I'll spend a few more minutes and then we can take a break after that. Okay, so the other thing that, you know, the same kind of exercise now you can repeat for different problems. So here's a problem where it's about kind of adaptation. Like you observe 2 classes, so circle classes and square classes. And then I ask you a question, pick a line that you like. So yeah, you could classify it with this blue. Thanks for commenting in chat. I feel like a YouTube celebrity right now, where I'm reading the comments and also talking at the same time. So this is awesome. So you could choose the blue line or the red line. The question is like, which one is better? And actually, most people in machine learning, if you kind of have learned maximum margin or stable classifiers, it looks like that this one, blue one, is the better one because it's kind of passing through the middle while the red one is actually really cutting the corner, right? But an important point to realize when looking at just the data in hand, that you don't actually know what's going on in the rest of the input space, right? So there's a lot of things that you don't know about the world. Maybe you are, you know, you just learned about, like, you know, digits 0 to 3, and you don't know about digits 4, 5, 6, 7 that's going to come in the future, right? Then at that time, it's very difficult to tell which decision is a good one. If you think about the data that you have in hand, blue seems to be the good one, but that may not be the good one when you want to go into a different situation, from a ukulele to a guitar. All your decisions would kind of fall apart. All right, so I just give an adversarial example here. To suppose that I got this data next. You see that this blue line is classifying, you know, is not classifying this square correctly. So this blue line is actually wrong, and this red line is the right line to get to, right? So you never know. In the previous world, you didn't know what's going to come in the future. But when we are actually learning as kids, this is kind of situation we are in. We don't know what we are going to do in the future. We don't know what the future has for us to learn from. And we want to be more flexible, to be more accommodating. And it turns out that the principle is again the same. If you want to not get hurt so much, then you should be a little bit more open person. You shouldn't sort of like commit to something, you know, doing machine learning when you're 10, you know, or, you know, some decisions that you make when you're young, saying that you want to be a rock star. Maybe that's too narrow and specialized. That's what your parent will say. But if you keep more your options, yes, you're overconfident. You keep your option open a little bit, then you know, you are you can adapt easily. Now it turns out that this flexibility, just give me a second, I'll get to your question then. So the flexibility sort of gives you, you know, a way to adapt more flexibility. And this is kind of written here in this through equation, I want to explain this, and I'll get to your questions after I finish explaining this, is that what you will do is that you will start with some kind of prior at first, and you will look at the data, the first set of data, I've called it D1, and then you normalize. So you rank everything, and then you see that this line, this blue line, that was blue line, is now very thick, meaning that it has higher score. And the line, this line that's going to be good in the future, we don't know right now, but it's included in the model. So it's assigned a very small probability compared to this main model. Sorry, I will get to your question just in a minute. Okay. What you could do is basically when you get the next set of data, now you see that these lines that you've drawn here, they will all be misclassifying the red points. So your classifier should be here. But now what you could do, you could take the same, your posterior as your prior. So you see that it's recursive. That whatever decisions you made before, they're all summarized with uncertainty in this distribution that's telling you that there's a spread. And then when you observe the new data, you can update the spread by using the same Bayes rule. So now this is with the second data, and you invoke the Bayes rule, and you get to the posterior now with both data included. Okay, so this posterior now will put more weight on this model because that's the best model out of all the one that I had shown. Right. So this is a very classic idea. It's been used in many fields, and don't have time to go over it, but but you see that always you have to compute these integrals because you need to take care of explanations away from the best possible explanation. So you don't want to just have one model, but you want to have many models, and you want to average over all those and then normalize to understand how they rank among each other. It's very this kind of idea is kind of always applied. So you observe some data, you do fitting, and here the shadow is showing the uncertainty region. Now you see that you leave a lot of room here to say, I could go either way. This data could go here, this data could go anywhere, right? And when I observe the new data, so sorry, this examples here, I could basically just collapse my uncertainty because now I have more evidence. So by having this uncertainty, I'm leaving the room for flexibility. Now, this kind of idea has been used in machine learning. So for uncertainty estimation in deep learning. So here you have an image. This is the ground truth. You want to classify sky, road, sidewalk, buildings, etc. You use a deep learning network, and it gives you an answer, but it's good, but it makes a lot of mistakes. Like sidewalk is misclassified. And if you just give this to the self-driving car, this prediction, it might be very deadly, right? The car might go into sidewalk. So these are the places where you're making mistakes. If you look into these uncertainty regions, they actually sort of look like this. It's kind of higher uncertainty shown with a red color. So you see that you're able to sort of detect that I don't know enough in this region, and I should be more careful with my decision. This is the kind of idea that's repeated again and again. So if you just use one model, for example, in this case, your lines are kind of squiggly because you can go either way. You could go like this here. You could go like with this curve here with one model. But if you average over many models, it's like having this big jury, not just one king. And these jury members are voting. And then they're voting, and then you average their votes, and you get a very smooth decision boundary here. Because here, you're not sure. You don't have data, so you should be very uncertain. But so these squiggly lines, they don't matter here, right? So if you do proper Bayesian stuff, then you get this benefit. So I'm not going to go into this slide, but there's a paper on showing how by just looking at some Bayesian criteria, you can tell what will happen in the future if you had a different test set and which model would generalize better. Okay, so I'll close with this and then we'll do questions, is that we have two types of method. One is deep learning, where you only learn one model, and the other one is Bayesian learning, where you learn a distribution over the models. Now, the two seem very different from each other, right? This side, in machine learning, if you only choose one model, you can handle large data, you can scalably train it because you're just looking at one network. But you cannot estimate uncertainty easily, and it's very brittle to dynamic problems where you want to adapt things, you want to do sequential updating, you want to avoid retraining. Then you cannot handle with this kind of deep learning. But you can see the issue that the algorithms look very, very different. So you would say, why should I look at machine learning from a Bayesian perspective? Bayesian perspective seems completely different from what I'm doing in machine learning. But that is what we are talking about today, to say that these two things are not that different. Okay, so stop now and do 5-minute question. Then we'll do 5-minute break, and then we'll restart with kind of looking into more details. Okay, so I can read some of the questions that people have written here. Blue, okay, so both lines are valid. So Blaze Cruz is saying both lines are valid. Which one is more valid just depends on the current information we have. Yes. Yeah, you're right in thinking about this, is that in this case, the two models are, they give you zero error, but you don't know which one will generalize better in the future. And you don't know the future. It's basically like thinking that you don't know what your test data would be. Maybe in the future, things change drastically. So you want to be open to that change. And the Bayesian probability distribution gives you that flexibility. How does the order of data? There's a great question by Pat Sharmai, and I hope you don't mind me saying your name. Which order does it matter? And this is a really important point. Actually, it doesn't matter in this case. So of course, there are some models where time is added as an axis, but in this case, we've assumed that all data is kind of IID sampled given the parameter with the same probability. And in this case, no matter which way you apply the rules of probability, they always give you the same answer. And this is an incredible property of probabilities. We'll see later on that the objective function that the Bayesian methods have, this objective function is actually strongly convex. So even if you're doing deep learning, the posterior distribution is always unique. Well, there's some clause here, some regularity condition, some prior condition, but the posterior distribution is often unique. No matter in what order you see the data, you arrive at the same answer. So it's very beautiful in that sense. How is random forest different from Bayesian deep learning? Many competent decision makers voting for the ultimatum. So this is a good point, that there are techniques like ensembles. There are techniques. So these are generally called ensemble methods, where there are many models that are predicting things, and then you average over those. And ensemble is always is a good thing to have, because you have diversity. And the difference between what a Bayesian ensemble would do versus a usual ensemble would do is that the Bayesian ensemble will maintain diversity according to the posterior probability. So there's a mechanism, and we'll see soon that when you write down the objective function, there's entropy in it. So the diversity is enforced through by adding entropy of the posterior distribution as a regularization term. So somehow it's trying to maximize the entropy, but then it's trying to collapse the width according to the evidence. And maybe this picture actually says it quite well. Here you see that you have an uncertainty. So the entropy is quite high in these regions, and then you observe the data, and now you need to get to the maximum entropy with the constraints of these data points. So you will collapse, but not collapse too much. You'll collapse just the right amount. So this amount is governed by the posterior distribution. And in many frequentist ensemble techniques, they will employ different techniques to maintain this diversity. And that's where these techniques differ. And my personal belief is that often the maximum entropy principle is the right principle. If you could do it, then that will kind of work most of the time. So many people actually try to do ensemble with this kind of Bayesian flavor, where you're trying to maximize the entropy. Sorry, I'm not able. Oh wow, there's a lot of questions here. I think what we can do is we could probably take. So it's 4:12 in my time zone. It's like 12 minutes past the time. I think in India it's slightly different. But how about we meet back in 8 minutes and then go over these questions, do some discussion, maybe finish this part, and then get ready for the next part. I hope that is okay. So I will see you in 8 minutes. All right. So I hope that break was enough, and we have about 40 more minutes left, as I understand. So looking at the questions, I think there are plenty, and I'm very happy with that. So I was thinking that we can try to do questions for maybe 10, 15 minutes, maybe even more, and then spend the next 20 minutes on this next part, the first part of it, where we start to look into the Bayesian objective. So I'll go through your questions now a little bit more. If you want to also speak up while I'm answering your question, if you want to talk, please do so. So there's a question by Ashish. So I could use a neural network for the point embedding as a substitute for a kernel, which would give me the advantage, disadvantage of introducing any kind of nonlinearity, especially when I do not know which prior is the best. Or would that remove the advantage of Bayesian learning? Yes, I think you can do this. So there's no problem with doing this kind of thing. So you could change the model class if you want to. The Bayesian aspect is sort of on top of all of this, is to think about uncertainty. But also remember that when you change models, you kind of change what you know. So that means that you change what you don't know. So the uncertainty changes. The posterior distribution is different. And this is like another kind of area to do transformation between these kind of different models that would require some work. But it's in principle, it should be fine. Okay, there's a question by Jerui Tao. I'm sorry if I'm pronouncing your name wrong. Does the prior affect the results significantly, and how do we choose prior in practice? So great question. Yes, the prior could change the result, because I mean, I think you could see it in any of these examples. Maybe this one is that because you're ranking things by multiplying the prior and the likelihood, if you say that your prior is very narrow, then you will score things differently compared to what you would otherwise, right? So it's that. Sorry, let me just kind of say a little bit more. So like here, for example, this is actually a good example to understand that your past knowledge is somehow concentrated in your posterior probability, and this posterior probability then become the prior for the next task. So you should also think about like as prior as an evolving quantity. So you start with something very vague, but the effect of it hopefully should go away as you observe more data. So you're right that the prior affects the result. But if you have enough data and if you're updating your prior by using this Bayes rule as your posterior, then I think you could be fine. But a care must be taken here. But a care is always need to be taken. For example, in deep learning, you have to somehow regularize implicitly or explicitly the problem to get a good solution. And right now, SGD does something, but we don't know what it does. So prior is always in play everywhere, even if people say that they don't actually have it. Sorry, somebody was saying something. Or, okay, that was maybe just some disturbance. It's fine, okay. I hope that I answered this question properly, but this is an important question, so we could come back to it later on. A question by Arun: are we performing probability of theta given D2 for each theta and choosing the argmax? And is the theta on the slide there a general form? So definitely not the first one. So we're not doing argmax, but so you can think of like theta, for example, in this case, you can think of it as slope of the line. And so you have a distribution. So your theta can go from like, you know, maybe in the real coefficient term, it could go from -infinity to +infinity, and you have a distribution over it. And that distribution has this form. So there's no extra thing that needs to be done. I think it may require you to do some calculations to convince yourself of how exactly this is written. And I would encourage you to look into Bishop's book, maybe. Just look at like Bayesian linear regression, chapter 3, I think. And that will kind of help you to understand what exactly this distribution looks like. Okay, next question by Igor Revkov. Is it true that sometimes a Bayesian approach can be simplified into a non-Bayesian framework for easier model training? Yes. So there is a technique called Laplace approximation, which is basically kind of, you do the non-Bayesian training, and then you get one theta, and then you try to look around that theta. So you kind of fit a Gaussian around that by using the curvature. And that will give you some idea of like how the region around it, how the flatness of the region around that point. And that is one way to use, a Bayesian methods from a non-Bayesian technique. And you could do this if you want. I hope that answers the question. So, oh, okay, sorry, Arun, I answered your question. I only reached the, so there's another question rejecting the previous question, but I didn't see that. So Yazan has a question of how Bayesian approach is reflected in real world implementation, that is how to switch between models in real application to attend to a new situation. Yeah, I think this is a good question. It takes a little bit more time to explain. A simple explanation. So I would encourage you to maybe look into David McKay's book. He has a chapter on model selection. He actually uses neural network to demonstrate that point. And if you don't remember the name, just ask me later, or maybe somebody could post in the chat. David McKay's book, you can look into that. You can, essentially, the simple answer is that you can apply Bayes' rule recursively. So right now, you're conditioning only on the data, but you can condition it on model, and you can rank models using the same law of probability. It's much harder there, but you can actually do it. So this paper that I showed before, this paper is actually doing the model selection. So these are models of different architecture. So this is like ResNet is these ones, CNN is these ones, and they have different number of parameters. And what we are actually doing right now is that we are essentially changing models, and we're evaluating which one is better by using something similar to Bayes' rule. I hope I'm answering your question right, but if I'm not, I'm sorry. Okay, so next question is by Chan. Seems Bayesian method use many models is more computation required than frequentist approach. Yes, that's right. So this is kind of the main point of this whole part, that doing Bayesian, you require doing this integral, and this is very difficult. It's not scalable. But in the next part, we're going to kind of rewrite this posterior integration, of probability in an optimization form. And then we'll see that the left and right, they're actually not that different. Okay. So eventually you can always kind of rewrite the problem and then show similarities. And that would be the next part of the talk. Hopefully we'll do that tomorrow. So there's a question by Talha. What is your confidence in aleatoric uncertainty estimation methods for DNNs? They're okay. So right now, I don't think we are anywhere close to understanding how should we do uncertainty estimates for neural networks, because neural network could fit whatever you give it. So it may be that there is noise in the data, but the neural network will still kind of fit it quite well. So it can't tell difference between the noise and the model. And so you need some kind of like regularization. So like entropy could be used in the Bayesian world, but we are not really doing exact Bayesian inference. So we introduce lots of error, and that's probably not good. But I can't say more than that because we still don't know the answer in the community. This question by you. Sorry, maybe I missed some content. So the Bayesian method could get the distribution of theta, and DL could provide the fixed value of theta. Yes, that's exactly what the point here is. So it's shown in this slide, as you can see. Okay, good. AS is asking, so can I ask the main takeaway so far is that Bayesian inference allows for one to model for uncertainty. Will this uncertainty eventually reduce? Maybe I don't understand the question. So main takeaway, the first takeaway is that the Bayesian inference allows one to model for uncertainty. Yes, so Bayesian inference allows you to compute uncertainty of a model. And the second thing is, will this uncertainty eventually reduce? And that is the yes. So that's the point, that as you observe more evidence, the evidence that is new evidence, that's not same as the old one. So, if you were to go back to this example here, if you observe more evidence here, it will only reduce uncertainty in this region. If you want to really reduce uncertainty globally, then you need evidence different from the old one. So when the new evidence comes in, the uncertainty reduces. At the old place, it will only reduce up to the noise in the data, and then you cannot reduce it further. Right? So that's aleatoric uncertainty. Sorry, I'm glossing over a lot of things here, but it's impossible to cover everything in this short time. Okay, can you explain why Bayes is not scalable for big data? I could say this again. It's essentially because of this integral. And I would kind of want you to think about theta, for example, as, a big neural network. So this P is a high dimensional integral over theta. So maybe 1 billion parameters. It's a 1 billion dimensional integral. And then you have maybe 1 billion data points. So this likelihood term, P of D, contains 1 billion products. Right, so because of that, this integral is extremely difficult to compute for big data. and big model. Okay, sorry, I'm not. Okay, wow, I'm almost reaching the end. So why is Bayes not scalable? It's due to the integral. Okay, so I think this is the one takeaway of this whole part, that you can do a lot of things with Bayesian methods, but you always get stuck at the integral. So people become non-Bayesian because of this integral. And what I want to show you in the next part is that, well, you don't have to write the problem as an integral, okay? It could be written slightly differently without this kind of integral. And there you will see that the methods are not that different. So you can actually recover the solutions that you would get by what you have in the right-hand side by using something that is on the left-hand side. So using Bayesian methods, you can still recover the same thing, maybe even reduce the computation to be the same thing. But then if you want to be Bayesian slightly, then you can increase slight computation and get some benefits from the left-hand side. And hopefully that would be that will be communicated to you by the end of the tutorial. If the data set, so Bhavani is asking a question, if the data set D2 is scaled differently from D1, do you think Bayesian approaches lead to a worse classification? Similarly, if D1 has noise and D2 does not have noise, how does Bayesian inference work? So yeah, question. There's in theory, there's no problem, because you can have two different likelihoods. Like if you know, maybe this is like digit 0 to 5, and maybe the right-hand side is digit 6 to 10. And maybe digit 0 to 5, you have more of them, and maybe 6 to 10, you have less of them. The Bayesian method would automatically kind of adapt with the uncertainty to this imbalance in data. So it's kind of like the rule, the Bayes rule, and this update using probabilities can automatically adjust for these problems in the data and the model. Now, this can only work until the specification of the model. Okay, so I would really want to tell you that it's not magic. So like if you didn't specify if you specified this model, so this is called Bayesian model, so it's a prior, and this is the likelihood. If the likelihood somehow is wrong, you cannot fix it. So if you thought that if the data was noisy in reality, but then you thought that the data is not noisy and you modeled it with maybe very small noise variance and trusted the data more, Bayes' rule cannot fix it. But you can apply the Bayesian philosophy recursively on top of it to estimate the hyperparameters, and that could actually help, right? So there is a mechanism to correct for these things, but it's not magic. Probabilities can do work up to model specification, and when you have model misspecification, then you need to work extra. Okay. It is not clear, so Rishikesh is asking the question, it is not clear why Bayes can't handle complex model. Yeah, so I hope that question became clear by now, because you could just think of like theta being a billion parameters, and this integral is really big, and there's no closed form expression for it. And if you don't have a closed form expression, you may try to do some Monte Carlo methods that would not work in the billion dimension, and your probabilities will not be correct. So of course, then you not do your accuracies, estimation accuracy is really bad. Okay, a comment. So comment by Manish, the posterior always have a lower uncertainty than either the prior or likelihood. I will not I think the intuition that you're getting at is right, that in general, the posterior should contract with more evidence. But these formal statements a little bit more tricky than just saying lower uncertainty. But I think the intuition is it's mostly correct that the entropy should reduce. And entropy, whenever you add a new information, entropy has this property that it does reduce. It is non-decreasing, I think. It's written in E.T. Jens' paper from 1957. If you want, it's the reference is in my short note. E.T. Jens, you can look at that. Okay, Siddharth has a question. Can we approximate the integral with some sort of sampling? Yeah, okay. I was just saying that. So you could use Monte Carlo method. So this is basically what I've written here is like that. You sample from the prior, and then you sample many. Maybe you sample 10,000, and then you score each of them and you sum them. So that will give you an estimate. But you could see that if your parameter, maybe if you have 10 parameters, then maybe you could do 10,000 samples, and maybe they'll be good enough. But if you have like 100 parameters, then you may need 1 million samples. And as the number of parameters increases, the number of Monte Carlo samples that you need it becomes quite unmanageable. So there are some results on this, and I'm not an expert to pull out those convergence rate numbers on top of my head, but these are basically governed by central limit theorem of how the estimate will become better. But they are usually not feasible beyond like 10 or 20 parameters. So they're not useful. Then there is these set of techniques that are called Mcmc, so Monte Carlo, Markov chain Monte Carlo methods. And there you try to not do random, sample everywhere equally, but try to sample more cleverly. And it's sort of, some of these methods are of the sequential nature. So there are these methods called sequential Monte Carlo. They really work in this fashion, that they would kind of update the probability sequentially. They'll choose some path, maybe through data, maybe through model, some kind of sequence where they will update things sequentially and make approximation in certain places. So these methods work quite well. But unfortunately for deep learning and neural network and many other machine learning problems, these methods have not taken off. Although, there is this method called SGLD, so Langevin dynamics method, and that method is quite popular, but it mixes very slowly, meaning that the samples that you get out of it, they're correlated. So you need to run it really, really long time to get an independent sample. And if you have correlated sample, then your estimate is not going to be good, because again, central limit theorem requires it to be independent. All right, so I'm okay. Good books and papers to get started in Bayesian DL. That might be a question. If you could send me an email, or I would probably send it for tomorrow. But thanks for asking. So this is great. I'm very happy that you asked so many questions, and I had really a lot of fun to answer those. So let's start with the question, and let's see how much time we have. So it's 42, so we have about 18 minutes. What I can do now is I can go through the first part of this, and we're not really behind time. I think we're just about, we're quite on time, so this is very good. So what the goal of the rest of the talk, now that you know Bayes and you kind of understand to some extent why Bayesian methods are difficult and why they look different from what you use in deep learning and machine learning, now we're going to try to bring the two worlds together. Okay, so we'll try to reformulate Bayesian inference in kind of the same term as machine learning. And we'll look at these objective functions. And then we'll try to go into their solutions, what kind of solutions they produce. And then we'll see how, usual machine learning one point estimate style solution can be recovered from a Bayesian solution. And then Bayesian solution has and more additional thing that can be useful. So that is the hope here, is to bring the world together to understand how this Bayesian principle runs behind many machine learning techniques. Okay, so this is kind of based on this paper that we did. So I gave a NeurIPS tutorial in 2019, and that was the first time that I kind of talked about all of these things. But then over the last 2 years, we tried to summarize those things in this paper, and you can find this in my webpage. So it really, the hope is to not really go through the paper. My hope is that I can tell you just enough so that you are able to read the paper later on. So I don't want to give you all the details of the paper. You can read it later on, but I just want to give you enough background for you so that you can actually go and appreciate it without kind of getting lost with lots of details. It's a very compressed and kind of dense paper, actually. Okay, so let's start with the first part, is how can we write Bayes rule. Looks very different from what we do in deep learning or machine learning. So how can we write Bayes rule as in that optimization problem that we have, like this minimization of loss function? It's actually quite straightforward. So here you see that there's like loss function doesn't appear directly, right? And I didn't really go through the details of how loss function is in here, but this slide will make it clear. By the way, I'm writing the details of this are in that paper, and you can go and read the particular section that's written here, like Appendix A for this part, and you can see the details that probably are missing in this quick presentation that I'll do. Okay, so let's say that the loss is actually this kind of the numerator of this. It's the score that we were computing. So remember that we sampled from the prior, we multiplied by the likelihood, and it's somehow log of that, negative log. So you could see that if the likelihood is defined with e to the power of minus loss, then loss would be basically negative of that, like log likelihood. So that's basically what I've done. And P of theta basically gives you the regularizer, like negative log of prior gives you the regularizer. So think of like a quadratic regularizer would give you like L2 regularizer would give you a Gaussian prior, and maybe mean square error loss will give you Gaussian likelihood. So that's how the loss is written here. And now what I'm claiming is that this integral, this Bayes rule, can actually be written as this optimization problem. Okay, so there are a couple of things happening here. First of all, I have this loss, so this numerator is in here. And now I'm not just minimizing the loss at 1 theta. I'm minimizing the loss, the expected loss instead. And the expectation is taken over a distribution that I denote by Q. So I try to say something different from P. It's just a symbol. So it's also a probability, but it's something that we can estimate. It's not the model. And so Q of theta is a distribution. And now what you're going to do, you're going to sample lines from this distribution. So think of like all those lines that you draw. And now instead of minimizing the loss at 1 theta, 1 line, you want to minimize the average over many lines. So do many models, take the average. So on average, samples from your distribution should fit the data well, should minimize the loss of the data. But if you just solve, so you're trying to now minimize over this Q, and you minimize in the space of all probability distribution. It could be any distribution function of any shape. It could put uncertainties anywhere it wants, but we want to minimize the expected loss. Now, if you just have expected loss, what will happen is that the distribution will kind of collapse to fit only on the data. But you don't want it. You want the distribution to collapse just right to keep uncertainty in the regions where we haven't observed any data. So for that, we add an entropy regularizer. And this entropy is what makes the Bayesian methods Bayesian. Okay, so this is really the central thing here. And so if you have this entropy, sometimes you have KL divergence, and maybe we'll get to that at some point. But what you're basically saying that out of all the distributions that minimize the loss or explain the data well, pick the distribution that has the highest entropy. Highest entropy meaning it has the highest spread. So basically start with like a very spreaded distribution and then shrink it until it explains the data well. Or fit the data well and spread it just the right amount to get the maximum entropy that explains the data well. Okay, so there are two ways to look at it. But this is really kind of maximum entropy principle. Okay, and the claim here is that this equation is equivalent to, is obtained by solving, by minimizing this problem. Okay, so people don't believe this. Many times, even statisticians, when I talk to them, Bayesian statisticians don't believe it because somehow this was not, you know, a very well-known formulation. And this was it has roots. So we'll get to that maybe later, but we'll get to the history of why this was not known to many people. But it's a very old result, in fact. But let's try to prove this first. So what I've done here is I've basically just written the entropy. So the definition of entropy is this. It's just the expectation of the log probability under itself. And then I have just collected the two terms. So inside the log, so it's log of Q theta comes from here. And then this is e to the power negative of loss, right? So this becomes the probability. And it's clear that this will be minimized when the numerator and the denominator are equal, because then it's log of 1, and log of 1 is 0. And 0 is the minimum. Actually, I mean, you cannot go below 0, but there's another explanation for why you can't go below 0. But it's like a divergence, and divergence is the minimum value of 0. I cannot explain that right now, but hopefully you can convince yourself maybe later on. But eventually you see that Q should be set to the exponential of the negative loss, right? And if I plug in the definition of the loss, which is the negative log probability, I get the optimal Q to be proportional to the score. So essentially, if I normalize the distribution, I will recover the posterior distribution, okay? So this is a very, very simple proof. What it actually says is that you can write the Bayes rule as a minimization problem, and things are, you know, still fine. And the minimization problem now looks like minimization of loss, but now you have a distinctive feature of the Bayesian principle is to have the entropy there. The nice thing is that this holds for any loss function. So right now I've written loss with log probability, but you can plug in anything that you want. It doesn't have to be a probability. And this thing also was not really appreciated in Bayesian community a lot. Also not known for machine learning community to many people. But this is the concept that we call generalized posterior, where the loss doesn't have to be exact probability. And that's why I call this Bayesian principle instead of Bayesian inference, because it doesn't have to be a probabilistic model. It could be a non-probabilistic model, and you can still compute probabilities on top of it. The history is actually pretty amazing. The original formulation is maximum entropy principle from 1957. And then a couple of papers in between. Zellner wrote this in 1988. Hinton's paper comes in 1992 on minimum description length, which is exactly this formulation. So we'll have a couple of slides on this and try to understand, go a little bit more into this. Is very fascinating to see that this view has been around but not appreciated that much. But it's being used in online learning and pack-based community as well. Sorry, somebody has a question, it seems. Okay, oh, there seemed to be a question that I didn't. Yes, so Igor has a question that we can go to the frequentist approach by basically throwing out probability and entropy. That is one way to do. So if you get rid of entropy and you get rid of the distribution, you are back to doing what you were doing. But this will kind of defeat the purpose, because what you want the principle to do is that when the probability is required, it should use it. And when diversity is required, it should be diverse. But when you say, I don't want the diversity, I only want 1 point estimate, it should also, the same procedure should give you that one value. So that is kind of what we are going to in the next part, okay? So without like having to change the principle by removing the entropy, we'll keep the entropy, but we'll show that still you can get the answers that you were getting before, but now you have some uncertainty for free along with it. Jerui has a question, and sorry if I'm pronouncing your name wrong. Can I regard this rule as a generalization of the elbow in variational inference? Exactly. So variational inference is often written with probabilities, so it doesn't directly accommodate loss functions. So generalized posterior is a slight extension, but variational inference is usually considered a subset of Bayesian inference. But this generalized posterior is slightly bigger than Bayesian inference. So I call it Bayesian principle, but some people call it generalized posterior. Some people call it Gibbs distribution, Gibbs measure, things like that. There are pack-based methods. There are many names for the same thing. Great. 5 more minutes we have. Let's see what we can do in 5 minutes. So, okay, so maybe I could just say some things about what we're going to do. So we're going to try to understand a little bit more the nature of this objective when we resume tomorrow. And we will then, okay, let me actually remember back. So then we'll try to look into the solution that you produce. So this side, the solution is usually you set the gradient to 0, gradient of loss equals 0. And this side, if you set the gradient of this to 0, you'll get something different. But then we'll compare these two and we'll try to see that actually these two are not that different, it turns out. So there are lots of like nice property in the Bayesian solution, but then you can recover the non-Bayesian solution from this quite easily. And we'll try to get into information geometry and Fisher information matrix a little bit to understand why this happens and why this is a general principle that being aware of this principle helps you to do better machine learning is what my hope is, my claim is. If anybody has any question, I can answer maybe one more question.
Sorry, can I ask with voice? I think it would be easier.
Go on, please.
Yeah, so I don't know how wrong is that. It's just the feeling I had for a bit. Looking at these formulas, can we say that the frequentist approaches, at least in this formulation, are kind of a subset of a general Bayesian framework or not? Because like left basically looks like the smaller form of the right. That's what I'm saying.
Yeah. So actually that's a good point. So often, let me say this is actually a good point, and I'm glad that you asked at this point. So you see here, right? Like what you could do, you could always choose Q of theta to be a delta, right? A delta distribution, like a Dirac delta, and then you could say, oh well, the right will collapse to left. But actually, it's not true. Because it's true if you have discrete supports, if theta was discrete, then it'll be correct. But for continuous parameter space, Q of theta, the entropy of a Dirac delta is infinite. I don't know if it's plus infinite and negative infinite, but it's not defined. Okay, so just by reducing the uncertainty to 0, right will not become left.
I see. Thanks.
So this is a very important point, and unfortunately I don't have the reference here, but there's a paper by Max Willing. I hope I'm and colleagues, I will write it in the chat. It's about latent variable models, pitfalls, something like that, and their pitfalls. I think it's a deterministic latent variable. It's cited in our paper, in this Khan and Drew, the Bayesian learning rule paper, so you can find this reference there. They have this explanation. It's published in 2008. It's a common misunderstanding to think that by collapsing distributions, you can just kind of make Bayesian methods non-Bayesian. There's many technical issues with doing that, and they arise in many different ways. Does it make sense?
Yeah, it does, I guess.
Yeah, it's a subtle, like, mathematical intricate thing that you cannot just kind of switch from. So lots of Bayesian people actually try to say that, you know, they're strictly more general because they can always do these things, but it's not correct. You know? Would the maximum a posterior be frequentist answer? There's a question by Manish, and it is a frequentist answer because it only gives you one answer. It's a probabilistic model, but it's only giving you one answer. And so when we say something is Bayesian, we should usually think of things as marginalizing, like integrating or summing things up. And map is not, really doing that thing. Of course, there's a range of things in between that, so I don't want you to be a hardliner about this, but right now we are really thinking about integration. Okay, so I think that's it. So I'm done.